Hello everyone, my name is Khalid. I would like to talk about skyhooks today in my video. As you see, I stutter. That is why I will be using an AI voice generator in my video. I hope you like it.
6, 5, 3, 2, 1, 0, and liftoff.
Going to space has always been challenging. It is not only technologically complicated, but very costly too, since only 1 to 5% of today's rocket's mass is only the payload. That is why a lot of approaches came up to solve this problem. In this video, we will discuss two of these approaches, mainly space elevators and skyhooks, with more focus on the second one. Before today's rocket system to carry cargo to space, one of the earliest known proposals for accessing the weightless environment of space was made by Tsiolkovsky in 1895. He envisioned a tower built at the equator that extends beyond geostationary orbit. A cable would then be attached from one side to it and from the other side to a ballast floating in space. Tsiolkovsky explained, "As one ascends the tower, gravity gradually decreases without changing direction. At a distance of 34,000 versts, gravity is completely nullified. Beyond this point, gravitational forces are reversed, pulling outward from Earth, causing a person's head to face downward toward Earth." 65 years after Tsiolkovsky, Soviet engineer Yuri Artsutanov proposed a new concept, a tower anchored in space to a satellite, extending downward toward Earth and touches it at the equator. This idea can be seen as a reversal of Tsiolkovsky's original tower, since a cable can be then deployed up and down from the tower to transport goods between Earth and space. Artsutanov was also the first one to address the challenges facing the manufacture of the cable, since it is required to have great strength and to hold great stresses along its entire length. His concept, which he referred to as a funicular, was intended to function as a cosmic elevator. He proposed a balanced energy system in which the energy gained from sending payloads down from the outer part of the structure would offset the energy needed to lift payloads upward from Earth. The system would allow for a lifting speed of around 1,000 kilometers per hour, enabling the transport of up to 12,000 tons per day. These two concepts evolved after that to be today's well-known space elevators. Building a skyscraper from Earth to space's lower orbit would be impractical because there is no building material available nowadays that can carry the weight of such a structure. Because of that, people came up with a much simplified idea, a cable that would be connecting Earth and a satellite orbiting it. Along this cable, an elevator will be operating to carry the cargo. Such a concept will reduce the costs of shipping to space significantly, since a recoup for the cost losses for a $20 billion space elevator would be just after launching 1,000 tons of cargo using the traditional rockets. The biggest challenge for a space elevator is the tether itself. It needs to be light, strong, and affordable. Theoretically, there are promising materials for such an application, like diamond threads and graphene, but there are doubts for this, since the tether must carry its own weight and the weight of the cargo in the elevator. It has to be able to withstand radiation, corrosion, meteoroids, and space debris too. Another challenge is that securing such a construction that extends for more than 2,000 kilometers in air would be an impossible mission, since it will always be a target for terror acts. A new concept for sending off cargo into space came up in the late 1960s, where a long tether connected to a mass, or satellite orbiting Earth, that spins around itself to generate a great centrifugal force to send off a cargo ship connected to its cable. This idea came up originally from the CIA fascinating project Fulton Skyhook system. During Operation Cold Feet, it was required to extract agents from an abandoned Soviet research station in the Arctic. The system used a helium balloon and a harness to lift personnel, who were then snatched midair by passing aircraft. While operating on such a smaller scale, the Fulton Skyhook demonstrated the feasibility of momentum transfer in aerial retrieval, a principle that underlies the cosmic skyhook. In 1966, Arthur C. Clarke and Isaacs et al. Published their well-known paper, Satellite Elongation into a True Skyhook. Their concept envisions a revolutionary method for transporting materials and payloads from Earth into space through a long, ultra-strong cable spinning in the Earth's atmosphere. Their concept represents one of the earliest serious scientific proposals for tether-based space transportation systems. The theoretical foundation is based on the fact that a satellite in geosynchronous orbit remains fixed over a point on the equator due to its synchronized rotational period with Earth. If a cable were extended from such a satellite both downward toward Earth and upward into space, the forces of gravity and centrifugal acceleration would be balanced along the cable. This would allow for a system in which the cable remains under tension, effectively hanging between Earth and space, and would be capable of supporting loads without the need for rocket propulsion. However, the implementation of such a system is heavily affected by the following factors. One of the foremost challenges in realizing the skyhook concept lies in the requirement for materials that combine extremely high tensile strength with low density. The cable must be capable of supporting its own weight over a length of approximately 36,000 kilometers, spanning from the Earth's surface to geostationary orbit, and potentially beyond, depending on the system's design. While some advanced materials exhibit promising strength characteristics in laboratory conditions, scaling up their production for consistent, long-length applications remains a major obstacle. In addition to material constraints, the system must contend with continuous tidal forces acting along the cable's length. Although it is small in magnitude, on the order of 10 to the negative sixth times Earth's gravity, these forces can induce oscillations over time. Without adequate damping mechanisms, such oscillations could grow and threaten the stability of the entire structure. To counteract this, active motion control, particularly at the cable's endpoints, would be necessary to dissipate energy and maintain equilibrium. Atmospheric drag presents another serious design complication, especially for the cable's lower segment as it enters the denser layers of Earth's atmosphere. At wind speeds reaching 200 kilometers per hour, the resulting lateral forces could cause substantial deflection, potentially as much as 45 degrees, if the system lacks a proper anchoring or stabilization mechanism. One possible solution is to suspend the lower end from a high-altitude balloon or platform, but this adds further complexity, particularly for deploying the cable and connecting it to payload systems or the surface infrastructure. The risk of collision with meteoroids and artificial satellites is also a significant concern. The cable would pass through multiple orbital regions, including zones densely populated with active satellites and space debris. A collision with even a small object could sever the tether, leading to potentially catastrophic outcomes. Severed segments might fall back to Earth uncontrollably, posing hazards to populated regions. The current concept does not yet offer a mitigation plan for this risk. Further complicating matters is the cable's exposure to the space environment. As it extends through the ionosphere and beyond, it encounters regions rich in charged particles, extreme ultraviolet radiation, and atomic oxygen. These environmental conditions can degrade materials over time, leading to structural fatigue, electrostatic buildup, and corrosion. At present, the long-term effects of these factors on the proposed cable materials remain insufficiently studied, adding uncertainty to the system's durability and safety. The deployment process itself is highly intricate. The proposed method involves balanced spinning of the cable from a geostationary satellite, with simultaneous extension of upper and lower segments. Successfully executing this requires precise control of tension, orientation, and growth rates. Ensuring that both ends of the tether remain properly aligned and balanced during the initial and subsequent stages of deployment is a daunting engineering challenge that has not yet been practically demonstrated. Power and energy management add another layer of complexity. Although the concept harnesses Earth's rotational energy to assist with launching payloads beyond geostationary orbit, energy is still needed to raise payloads up to that height. Efficient systems must be designed to deliver power to climbing vehicles and potentially recover energy from descending ones. Managing this bidirectional flow of energy while maintaining structural and dynamic stability complicates the system architecture. Lastly, the ground-based anchor must be engineered to withstand enormous mechanical loads. It will need to resist not only the vertical tension from the cable's mass and ascending payloads, but also lateral forces from wind and dynamic disturbances. The anchor must also handle transient forces generated during acceleration and deceleration of climbers or induced oscillations, making it one of the most critical and potentially vulnerable components of the entire system. Skyhooks as a structure to send off cargo from and back to Earth is one of many applications a tether can be used for. Among these applications, we will go through some of which got tested comprehensively. This can show us the behavior of a tether system in the real space conditions. In 1966, the Gemini 11 and 12 missions carried out the first experiments involving the use of tethers in space. The Gemini program explored two primary modes of tethered space vehicle operations. In the first mode, an angular velocity was deliberately induced in the tethered system using the spacecraft's propulsion system. In the second mode, the vehicles were allowed to drift while tethered, focusing on the effects of Earth's gravity gradient on their motion. Both modes of operation were successfully demonstrated, confirming the validity of the models and their calculations. Back in 1996, NASA came up with the idea of generating electricity from the magnetic field of Earth. This is similar to generating electricity by passing a coiler between the two poles of a magnet. It had a base satellite, a sub-satellite, and a 20-kilometer conductive tether connecting the both of them and acting as a wire. Using the ions in the ionosphere, NASA designed a system to create a system of electrons flow that would be able to generate electricity. Upon deployment, a small defect in the insulation material near bottom led to a large arc that melted it and led the tether to snap away from the spaceship. The tether could be seen all over the world in Australia, Hawaii, and southern USA. Few weeks later, it re-entered the Earth's atmosphere and burned there. This incident shows us how vulnerable the system is to such very small mistake that can cause its collapse.
If you think this takes skill, imagine trying to lasso a satellite in space. Now imagine flinging that satellite up to a higher orbit. That's what a small business in Linwood, Washington is planning to do. The researchers and engineers at Tethers Unlimited Incorporated, or TUI, are not cowboys, but they are developing lassos, new systems that will be used to capture as well as launch spacecraft.
In one application, it's sort of like a lasso or more like a sling, where you'd have a very long string or cable in orbit that's rotating as it orbits around the Earth, and it could swing down and pick up a spacecraft in low orbit and then carry it up and toss it into a higher orbit.
For founder Rob Hoyt, it all started while he was still in graduate school. He shared an interest in space tethers with Dr. Bob Forward, and the two eventually formed the company. Not long after, TUI began working on a NASA project with an award from the Marshall Space Flight Center through the Small Business Innovation Research, or SBIR program. The company developed the Hoyt Tether. With multiple interconnected lines, the Hoyt Tether is like a giant fishnet stocking. Today, TUI is collaborating with the Air Force Research Laboratory to refine the Hoyt Tether. A few years later, Marshall funded TUI to continue its work. The company then created the Terminator Tether, a cost-effective method for removing space debris.
It can deorbit the spacecraft with a much lower mass requirement than a rocket. And also, the tether system is basically self-powered, so it can deorbit the spacecraft even if the spacecraft is dead.
As we saw, these challenges underscore the complexity and ambition of the skyhook concept. While the underlying physics suggest feasibility in principle, the technological and engineering barriers remain formidable. Significant advancements in material science, structural dynamics, environmental resistance, and control systems will be necessary before such a structure can transition from theory to practice.